Let's talk about the first law of thermodynamics. You're probably familiar with the first law of thermodynamics, actually, and it probably, to you, means something like the conservation of energy. So energy cannot be created or destroyed. Energy must be conserved, that sort of thing. And this is, in fact, a true statement of the first law of thermodynamics, but it's not exactly the way that we will approach the first law in this course. We can connect these two things, though, by remembering that the entire universe can be described as the system that we are interested in plus the surroundings. So the system and the surroundings together make up the entire universe. The first law says that if energy leaves the system, it must be accounted for basically in the surroundings, or if energy leaves the surroundings, it must be accounted for in the system. So the change in internal energy of the system plus the change in internal energy of the surroundings has to be equal to 0. That's one way of writing the first law of thermodynamics. In this course, though, we're more interested just in what is going on with the system, and so we will in a way that accounts for the energy changes that occur for the system. So we will write this as delta U, and really this should have a subscript here of system, although we will generally leave this off. But the change in energy for the system is equal to the sum of all of the different energies transferred across the boundary. And these can occur basically in 3 ways, so that we can write the delta U of the system is equal to the heat that flows into the system. So Q is the heat flow into the system. And the direction is important here in that it's coming into the system. And we also can have energy transferred to the system through work, and this is mechanical work, and we're going to define this so that this is the mechanical work done on the system. On the system by the surroundings. And we can also then have energy transferred into the system through other kinds of work. And we'll talk in a few minutes about what those are. But they are the kinds of work that make the system complex as compared to simple. So this would be other work. Now, I mentioned that we're going to write this as plus W and define it as the mechanical work done on the system. This is the way that the textbook by De Hoff does this, and so we're being consistent with the book. However, this is done differently in Gaskell, so if you are following along with Gaskell, you'll notice that he uses a different nomenclature for this. So let's talk a little bit more about this idea of internal energy and the first. So the internal energy is actually what we measure for our system. The internal energy is a state function, so it depends only on the current state of our system. In contrast, Q and W are both process variables. So these only have meaning if our system is undergoing a change, but not when our system is in some particular state. So we cannot say that our system has some heat. It doesn't have heat, it only has internal energy. That internal energy might have gone up or gone down because of a heat transfer, but we cannot say that our system has heat. An analogy to this would be to think about the water in a lake. So let's say this is our lake over here. So the water in the lake is the analogy to you. We can talk about how that water got there. So some of that water might have gotten there from rain. Some of the water might leave the system through evaporation. Water might have come into the system from streams, let's say. It could have come into the system from the ground or leave the lake through the ground. But we can't say that there's a certain amount of rain in the lake. We can only say that there's water in the lake that got there through rain. Similarly, we can talk about the internal energy of the system that might have gotten in there from heat transfer or work, but there isn't a certain amount of heat in there. Thermodynamics, which again we write like this, can also be written in the differential form if we're interested in incremental changes in the internal energy. And that would look like this. Now, because Q and W are not state variables, we cannot write their exact differential. For U, we can write the exact differential, and that's why we use this little d. Over here, these deltas really just represent an incremental change. In that property. So we have some idea of what heat transfer is. Let's just finish up here by looking at what is work, this W term. So mechanical work is related to changes in the pressure and volume, and because we defined it as being the work done on the system, we actually have a negative sign here in our definition. So W is the work, P is the pressure, and V is the volume. So it's related to the pressure and the change in the volume. And we put the negative sign here so that if delta V is less than 0, which means that the system got compressed, that makes dW greater than 0. So work is done on the system. That's how that definition works. And finally, we can look at some other kinds of work that we might have. So other work terms which would contribute to that W prime, and those would be things like stress and strain, or if we had a magnetic field and a resulting magnetization. These come in pairs, you'll see, and it turns out that if you multiply their units, you end up with units of energy. Dynamics, just to summarize, we have delta U, where U is the internal energy of the system, is equal to Q, the heat transferred into the system, plus W, the work done on the system, plus other work terms.